Welcome to my channel. I'm excited to give this um, lectures today. This STEM cafe where we make everything science, technology, engineering, and mathematics comprehensive, entertaining, ease, enjoying, and assimilating. We teach so that you can find it very easy and fun, handling everything under science, engineering, technology, and mathematics. Today we are going to deal with a topic that is very fundamental, and the knowledge of this topic makes everything in STEM very easy and enjoying to handle. The topic is called dimension. The topic is called dimension. We all know when we refer to dimension of a quantity, we talk about units. But in these dimensions, we are trying to talk about how we derive that units, how these units are related to fundamental physical quantities of length, mass, and then time. Okay, let's write. So now we can now say that dimensions is the way physical quantities are related to fundamental physical quantities, mass, length, and time, denoted as M, capital L, and capital T, respectively. So what do we mean? All the physical quantities, we try to relate them to this so that we can work on them to get their units. So these dimensions is not about just the magnitude, it's about the units that we are talking about of each different physical quantities. Now, this is to denote nature of physical quantities encountered, referred to as units or measure of the physical quantities. Like when you are talking about area now, you talk about length times breadth, and unit of length is meter, and that of breadth is meter. So you can say L times L. So you have, okay, let me make this length breadth. So that will give you L squared if you are talking about the dimension. But the unit will be M squared, meter squared. So you can see. So when we want to work with dimensions, we talk about this one. When we are talking about the units, this one will now translate to the units. So dimensions make our work very easy, and we'll be able to know which quantity to attach to each other. It helps a lot when you are working, because you look at it as, I cannot add force to volume, I cannot add area to density. You cannot do that. So when you are working it, you should be able to think along the line that, what is the unit of these quantities I am gathering together? So it helps in our research work and in finding the accuracy of the quantities we are gathering together to form an equation. You will see as we go along. Now let's look at the application. We can use it to get dimensions of physical quantities and formulas relating different quantities when mathematics is difficult, e.g. in hydrodynamics. We can also use it to check correctness of dimensions and units. We can also use it to check correctness of dimensions and units in one place. Like this. If you have something like S equals UT plus half AT squared. This one is correct algebraically. But if you are just using this one now, if you write mistakenly S equals UT plus AT squared, if you check this out, dimensionally is correct. But if you look at the algebraic sum, this one is wrong algebraically. Wrong. So you can see. So that is the extent that these dimensions can take us to. So when we are talking about physical quantities, generally, we talk about vectors and scalar. So any of them, they must have units. And these dimensions help us to really be able to get the units or which one to combine together to get a different quantity. Now let's work some examples so that you will see how interesting it is and how it can help you out in different situations. Now, example. Let's look at if we want to find the unit of density. Density is mass per unit volume. And if I want to look at it, this one is rho. And the units from dimension, what is for mass? M. For volume, L raised to power 3. So I can say M, L. So what is M now? Kilogram. So the unit of this one is going to give me kilogram per meter cube. So you can see. So dimension makes open your eyes quickly to know, especially when you have multiple choice question. You can easily find the unit of a quantity if you know the relationship to another physical quantity or fundamental physical quantity. It is very easy. Let's look at pressure. You are asked, out of all these options, give the unit of pressure, and you are given some options. From definition, you know that pressure will be equal to force per unit area. Let's see. Perpendicular area. So now you have force per unit area. Then you can now say P is equal to, what is force? Newton. What is area? Meter square. So that will give you this. So if another quantity is related to pressure and you need to break this down, you can easily do it. So this will give you what is Newton. This one is force, and force is mass times acceleration. So that will give you M. And what is acceleration? L-T. That is acceleration. And what is M? This one is L squared. You can see. So you can also have a unit which can be something like this while you are working. So it makes you to be able to really interrelate physical quantities when working on them. Now I'll give you some examples. Now we have this in the gas equation. P plus A over B squared, brackets, into bracket D minus B equals to RT. What are the dimensions of the quantities A and B? So we have said it that dimensions make us to be able to know that the quantities we are adding together are of the same units. So in this instance, B and D are added together in a bracket alone. So it shows that the unit of B is the same unit as the volume as the unit of B. So unit of B is equal to is equivalent to L cube. So that of the dimension of B is L cube. So dimension of B is equal to L cube. So let's look at the other one. So unit of P, which is pressure, is Newton per meter square. And the dimension of P is, this one is kilogram meter per second square. So I have, this one is going to be M L C raised to power minus, because force is mass times acceleration. And I'm going to divide again with L. So it will be M L minus 1 C minus 2. Now for A dimensions of A over V squared is the same thing as this one now. M L minus 1 C minus 2. And you know that this one is L raised to power 3 squared. So for A now, therefore A over L squared will be equal to A over L, and it should be equivalent to this. M L minus 1 C minus 2. So dimension of A M L minus 1 this power 6, yes, because this one multiplies this. C raised to power minus 2. M L raised to power 5 C raised to power minus 2. So you can see we found the dimension, but this place now we have not really spoken about units. Please, this is dimension. We can just try to evolve or get units from dimensions. So here we just talk about dimensions of A. When we want to get the unit, we go a bit further. Now, suppose for a simple pendulum, the period T of oscillation depends only on mass m of the bulb, length L of the thread, and G, acceleration due to gravity, and T is equal to K m raised to power x, L raised to power y, G raised to power z, where K is a constant, which equals to 2 pi. Find the relationship between T and other quantities M, L, and G. Let's see how we go about this. We know that the unit of, we know T. Now to get this relationship, we look at the dimensions and bring them together. Let's look at this. T, you know that is period of time. K is a constant, so we don't need it. M, that is mass. L, that is length. G is acceleration. And the unit of acceleration is meter per second squared. So the dimension will be L C raised to power minus 2 Z. So what do we have at the end of the day? We have this M L L T. So we can still say further that T is M raised to power x, L raised to power y plus z, and T raised to power minus 2z. Now, let us look at the power of M on both sides, equating powers of M. Powers of M, you can see 0 equals to x. Therefore, x equals to 0. Equating powers of T. Powers of T. So we have 1 equals minus 2z. So z is equal to minus 1 over 2. Let's equate powers of L. Equating powers of L, 0 is equal to y plus z. And we know that z is equal to minus half. So we should give us y minus half. So therefore y is equal to half. You can now relate it to be T equals K, referring back to this equation. And we know that the power of M is equal to 0. So that one is out. What is Y? Y is half. So we have L raised to power half and G raised to power minus half. And we know that will be T equals to K into root of L over G. So T can be stated to be 2 pi root L over G, because you have been told that K is constant, which is 2 pi. So you can see it helps us to come around and get our relationship between T, M, L, and G. Example: velocity of transverse wave in a string depends on the tension F in the string, its length L, and its mass M. Suppose that V, that is the velocity, equals K F raised to power X, L raised to power Y, M raised to power Z, and K equals to 1. Find the equation relating V and other quantities. So we can start by saying V equals K F raised to power X, L raised to power Y, M raised to power Z. So the dimensions, we know the dimension of V is meters per second, and that is L T raised to power minus 1. The dimension of F is Newton, because it's the tension, and that is mass times acceleration, and that is M L T raised to power minus 2. L is L and M is N. Therefore, you can say V, you can relate them by saying L T raised to power minus 1 is the same thing as M L T minus 2 raised to power X, L raised to power Y, and M raised to power Z. We can further by saying L raised to power X, L raised to power Z, L raised to power X, L raised to power Y, and C raised to power minus 2x. You can see the relationship now. So it's very easy now. You can now see is M x plus Z, L x plus Y, T minus 2x. Now let's equate the powers. Equating the powers of quantities. Let's start with T. For T, minus 1 is equal to minus 2x. Therefore, x equals to half. For L, 1 equals to x plus y. And we can now see that y equals to half. Now for N, 0 equals to, we have already found, okay, for Z now, x plus Z, which is half plus Z. From this, you can deduce that Z is equal to minus half. Therefore, G is equal to K. What is our X? F raised to power half. What is our Y? L raised to power half. And what is our Z? N raised to power minus half. So V is equal to K root of F L over N. FL over N. So this one can still be written as V equals to K F root F over M, which is V, and we have seen that K equals to 1 over force per, that is mass per unit length. So you can now see that the velocity in the string, the velocity of transverse wave in the string velocity of transverse wave in string is equal to square root of the tension over mass per unit length. So you can see what dimension has helped us to achieve. Which of the following are scalars 1 and 2 vectors? Obtain dimensions of each. So let's look at this. A is momentum. Let's call this one vectors. Dimension. Scalar. Dimension. So this one now, we have momentum, we have force, we have weight, and we have acceleration. Here, scalar, we have work, speed, energy, mass. So very easy to go by. What is the definition of momentum? That is mass times velocity. So we have m(L)c minus 1. Mass times acceleration. That is m(L)c. Weight. The unit of weight is the same thing. So we have m(L)c. Acceleration is l(c). Now let's go to work. Work is force times distance. So we have it to be m(L)² c minus 2. Multiply this by distance. Speed is L(t) minus 1. L(t) minus 1. Energy, the unit of energy and this. For energy, the dimension is the same thing as that of work. m(L)² c raised to power minus 2. Mass m. So you can see from this that dimensions can help us to the extent of getting the units or close to the units, but cannot differentiate if the quantities are either scalars or vectors. It is our knowledge about the quantity, if direction or sense is important in defining the quantity. That is how you will be able to differentiate if a physical quantity is scalar or vector. How do I mean? Look at this. If you are talking about speed, we put it here, scalars. But speed and velocity, they have the same unit. When we are considering speed, we don't talk about direction. But when we are talking about velocity, we talk about direction. So dimensions has not really been able to differentiate between vectors and scalars. The volume per second of a liquid flowing through pipe of length L is given by K P A raised to power x over L mu, where K is a constant, P is excess pressure, A is radius of the pipe, and mu is a frictional quantity of dimensions m L raised to power minus 1, T raised to power minus 1. By dimension, find the number x. So we have this volume per second, P over T is equal to K P over L. So we have, what is the dimension for V? L raised to power 3. For T, we have it is equal to, so you can say it is same thing as P. What is the unit of P? That is Newton over area. And what is that of Newton? Okay, then that will be area. A is L raised to power x. And we have L, and we have this quantity too. M L minus 1, C minus 1. Let us break N further. That is kilogram times acceleration. That is M L C raised to power minus 2. And what is A? L raised to power 2. And we have L raised to power x, because A is a radius. A is radius. We still have L n raised to power n L minus 1 C minus 1. So we can now conclude that L cube C minus 1 is the same thing as this one. This one cancels this. So we can start by saying M, so we cancel this. L here, this one, and this one will cancel because of the power. This one is L minus 1. It remains this one, L, and this one. So we have L raised to power x minus 1. This one remains. And we have T raised to power 2, T raised to power minus 2 plus 1. So which will give us L raised to power x minus 1 and T raised to power minus 1. So if you look at it, equating powers of L. So 3 will be equal to x minus 1. Therefore, x is equal to 3 plus 1, which is equal to 4. So we have been able to find x. X is equal to 4 using dimension. Now let's look at this example. It says the period of vibration T of a liquid drop is given by T equals K raised to power x, rho raised to power y, gamma raised to power z. Where K is a constant, A is the radius of the drop, rho is the density of the liquid, and gamma is the surface tension of dimensions n C raised to power minus 2. Use dimensions to find x, y, and z. So let's write it out. T K raised to power x, rho, gamma raised to power z. Now let's look at what's the dimension for A. Dimension for A, since we know that is the radius, is L. What is the dimension? We have the dimension of this gamma. We are told that this is n C raised to power minus 2. And dimension for rho, which is the density. And we know density is m L raised to power minus 3. Where m is for mass and L is for length or distance. So since volume, this is for volume. Now we can now say T. This is constant. We don't need it. L is for x, rho, that is n L minus 3 raised to power y, and n C minus 2 raised to power z. Now let's expand and bring everything together. You can now say T is equal to L raised to power x, m raised to power y, L raised to power minus 3y, m raised to power z, C raised to power minus 2z. So you can see. Now let's gather the like terms. You have m x, you have minus 3y, m y plus z, and then c raised to power minus 2z. So we can now work on each, equating the powers. Let's take it in terms. For T, 1 on the left side is T raised to power 1, and on the right side it is minus 2z. Therefore, z is equal to minus half. Let us now work for that of n. For n, you can see it is 0 on this side. So we have 0 is equal to y plus z. And you know z is minus half. So y is equal to half. For L, you can see it is 0 on the left side. So we can see, and what is y? Y is half x minus 3 into half, which is, so therefore x is equal to 3 over 2. So the relationship now, you can now see the relationship to be t. Okay. So we have to find x, y, and z. So let's look at it. X equals 3 over 2, y equals half, and z equals minus half. So that's where we have to stop. That's where we have to stop. Now the question is, a body moving through air at a high speed v experiences a retarding force F given by F equals k a rho v raised to power x, where a is the surface area of the body, rho is the density of the air, and k is a numerical constant. Deduce the value of x. We are now given a sphere of radius 50 mm and mass 1.0 kg falling vertically through air of density 1.2 kg per meter cube attains a steady speed of 11.0 meters per second. If the above equation then applies to its fall, what is the value of k in this case? We have a relationship of this form. F equals ka rho v raised to power x. And what is F? So you can see F is retarding force. So the unit of F is Newton, and that is kilogram meters per second. That is ml c raised to power minus 2. K is constant, so we don't need it here. 0. A is area, surface area. That is m raised to power 2. Rho is density, and that is kilogram per meter cube. That is m L raised to power minus 3. And V is the velocity. V is the speed. So that is L t raised to power minus 1 raised to power x. So you can see. Let's go. So we have m L t raised to power minus 2. So we have this one. L raised to power minus 1, m, so L raised to power x, c raised to power minus x. So we have m, L raised to power x minus 1, c raised to power minus x. So if you equate the powers, equating power of c, minus 2 is equal to minus x. Therefore, x is equal to 2. So the equation is F equals k a rho v raised to power 2. So that's the answer. Now we are given some values to determine what k is. That is the constant. So we have F. We are given F, and you know when the velocity is constant, the retarding force equals to weight of the falling body. And what is that? mg. Here g is acceleration due to gravity. Acceleration due to gravity. We have the density, we have it, we have the velocity. Let us now find the area. We know the radius to area is going to be 4 pi r squared, and that's going to be 4 pi. What is 50 mm? 50 all over 1000 squared. What it is mm. Therefore, F, that is ng, is equal to K times 4 pi 50 over 1000 squared times 1.2 times 11 squared times 11 squared. And we are given the mass, that is 1. And let's take G to be 10, which is 10 meters per second squared. So this is 1 times 10 is equal to K times 4 pi 50 over 1000 all squared times 1.2 times 11 squared. So K is equal to 10 times, well, this is going to be 1 over 20 times 400 divided by 4 pi times 1.2 times 121. And that is going to give us, and that is equal to 2.1922. It's a constant, approximately 2.2. So you can see how interesting this is, and it's very important. It makes our work easier and easy to understand, or to get through certain points where it seems to be, or to, let me say, breaking codes, where it seems like, oh, this thing is looking hard, but when you look at it from this perspective of dimensions, you get it easily. So I hope you enjoy it. Kindly subscribe if you have not subscribed, and comment, please. I appreciate all your comments. So this topic we have treated today will be like stepping stone to other topics that we will treat later and enhance our understanding. Once you subscribe, share, anytime we have any new topic treated, you'll be among the first to know about it. Thank you very much. We appreciate you.